Welcome everybody! In this video, we will be doing multiple examples on how to use mathematical induction to prove our theorems. Our first example is to prove the formula for the series of k squared. This series is equal to all of the integers squared and them added together. And we're trying to prove the formula that it will work when the sum is equal to n times n plus 1 times 2n plus 1 over 6. Now, how can we use mathematical induction to prove this equation? Well, our first step is to see what happens when n is equal to 1. This is just the simplest. We're starting from the basics, and we could call this our base case. When n is equal to 1, let's see what the left and right hand side of the equation turns out to be. On the left hand side, we just have 1 squared. And on the right hand side, we have 1 times 2 times 3 over 6. As you can see, both sides turn out to be 1, so the equation is true, which means that when n is equal to 1, formula is true. Okay, so n equals 1. In that case, the formula is true. Now we're going to assume this formula is true for any positive integer value of n. So we're going to say that n is equal to a value. Let's call it a. And a is a natural number, because it's just a positive integer. Under this assumption, we're going to see if this formula will hold true when n is equal to k plus 1. This is saying if n is equal to any integer and the equation holds true, will this directly cause the following term, when n equals a plus 1, to also be true? Well, let's see what happens when n is equal to a plus 1. We have our sigma, k starts from 1, and ends up to be a plus 1. We're replacing the n with a plus 1. This series reaches all the way up to a plus 1, but in it includes the series all the way just up to a, plus our last term, which is the a plus 1 term. And we're working under the assumption that the equation is true when n is equal to a, which means that over here, we can rewrite it as our formula, which is a times a plus 1 times 2a plus 1 over 6. And then we finally have to add on our final term. Now we're going to take what we have here, this equation, and try to put it into a format of this. Something times something plus 1 times double that something plus 1 over 6. So our end goal should look something like this. N is equal to a plus 1. So we should have a plus 1 times a plus 2 times 2a plus 3 over 6. That should be our end goal. Well, first we have to factor out a 1/6 and an a plus 1. So look, we can factor out a plus 1 from both of these terms. And we can also factor out a 1/6. So after that, we will be left with a times 2a plus 1. And in our second term, we're left with 6 times a plus 1. And now we're going to continue to factor. A plus 1 over 6. Inside the brackets, we can go ahead and expand. we are left with 2a squared plus 7a plus 6. This bracket can be factored into a plus 1 over 6 times 2a plus 3 times a plus 2. So now let's compare what we have to what was our supposedly end goal. We can see that they are the exact same, which means that we have simplified our original sigma notation when n is equal to a plus 1 into a format of our formulas, n times n plus 1 times 2n plus 1 over 6. Which means that when n is equal to k plus 1, the formula holds true. So our final step is this type of logical reasoning. If the formula is true for n plus k, this was our original assumption, we found that under this assumption, it would be true for n equals to k plus 1. So this is our final conclusion. Because in the very beginning we proved that the formula is true for n is equal to 1, it means that n would be true for 1 plus 1, which is 2. And because this says that the formula is true for 2, then it would be true for 3. So the cycle keeps going on and on. It's like a stack of dominoes. As long as one value of n is true, all other positive integer values of n are true. So we have proved, using mathematical induction, the formula for sigma k squared. Now let's try to prove this equation. The sum of the series k cubed can be written in the form of 1/4 times n squared times n plus 1 squared. K is equal to all of the positive integers. So our first step in using mathematical induction is our base case. When n is equal to 1, what will happen? Well, when n is equal to 1, on the left side of the equation, it can be rewritten as 1 cubed. And on the right side, we have 1/4 times 4. So when we simplify, we see that both sides of the equation equal each other. So the equation is true, which means that when n is equal to 1, equation is true. Well, now let's assume that n is equal to any positive integer. Or you could call it any natural number. And under this assumption, we're going to see what happens when n is equal to the next term over, is equal to a plus 1. When n is equal to a plus 1, we can rewrite our equation as k is equal to 1 all the way up till a plus 1, k cubed. And this series has the series k equals 1 till a in it. But it has one more term, which is a plus 1 cubed term. So we are working currently under the assumption that when n is equal to a, this equation holds true. So we can rewrite this sigma using the equation, which is 1/4 times a squared times a plus 1 squared plus a plus 1 cubed. Now let's see if we can modify this equation and put it in a format where it's similar to the 1/4 times n squared times n plus 1 squared. Well, first, we need a 1/4. So let's factor out a 1/4. We're left with a squared times a plus 1 squared plus 4 times a plus 1 cubed. And now we're going to try to factor out a n squared term. In this case, n is equal to a plus 1. So we're going to factor out an a plus 1 squared. We would get 1/4 times a plus 1 squared is equal to a squared plus 4 times a plus 1. We could go ahead and simplify what we have inside the square brackets. We get a squared plus 4a plus 4. This is the same thing as 1/4 times a plus 1 squared times a plus 2 squared when we factor our parentheses. Looking at this format, it is the exact same as what we have in the equation we're trying to prove. In this case, n is equal to a plus 1. So, under our assumption that the equation is true when n is equal to a positive integer, a plus 1 will always also be true, which means that now when n is equal to any positive integer, this formula will be true, and the following value for n will also make the equation true. Thank you for watching, and I hope you learned something from this video.